All right, your notes probably say section 6.6, right? And obviously, chapter 6. So most likely, with this absolute value equations and inequalities section, probably looking at, at least near 2018, 2019. 6.6, and this is, at least these days, the final little section in chapter 6 before we get set to take an exam, a chapter exam. And and this whole chapter has basically been about mostly inequalities, less thans, greater thans, all that kind of stuff. We're gonna do a little bit of equations here, I suppose. It's going to still be mostly an emphasis on inequalities, I suppose. Like when it comes to the test, okay, but the key here is that we're going to be saying, what the heck, when absolute value is thrown into it, like if you have absolute value involved in an equation or an inequality, what does that pretty much mean is going on? So let's look at absolute value equations. So look at this simple thing, okay? Can you list the solutions to this? What could x be to make this true? The absolute value of what equals 5? What number in for x would make that true? Well, obviously the absolute value of 5 is equal to 5, but also what? The absolute value of -5 is also 5. So there's actually two numbers that you could say are solutions and would make this true. X could be 5 or x could be -5. And then you kind of just maybe we take it up a notch here. Can we list the solutions to the absolute value of 2x minus 4 equals 12? And to cut to the chase, think of 2x minus 4 as like one final result, one final quantity, you know what I mean? So think of it this way. The absolute value of 12 equals 12, or the absolute value of -12 also would equal 12. So basically, 2x minus 4 could basically be 12 in disguise, or that entire 2x minus 4 could equal -12. If that entire 2x minus 4 equals 12, or the entire 2x minus 4 is equal to -12, then the equation would make sense. So you would literally write that. 2x minus 4 is equal to 12, or 2x minus 4 is equal to -12. And from there, you can just solve each one of these separately for x, because at the end of the day, you're solving for x, not for 2x minus 4. We can start with what 2x minus 4 must equal, but at the end of the day, we want to, add 4 to both sides, divide both sides by 2, both here, and end up with +8 or -4 is like your final two answers. And this helps us see what's inevitably going to be like your overall strategy solving these absolute value equations. Let me see if I have anything. Okay, not so much. So look, so your overall strategy is going to be like this. The first thing you want to do is make sure that the absolute value portion of your equation is the only thing on the one side, on let's say the left side. So once you have your absolute value part isolated, you can split it into two separate normal equations. In this case, one of the equations was going to be set equal to +12, and the other case was going to be set equal to -12. one of the teachers I work with pointed out that there are two vertical lines that denote absolute value. There's two vertical lines, which means there's going to be two cases. One where it's equal to positive 12 and one where it's equal to negative 12, and then you can solve each one. So in this example, the absolute value part of it would be the absolute value of 4x minus 1. So like this says, it says get the absolute value part alone first, then split in two cases. So here, the first thing I would actually do is get this minus 5 away from that entire side by adding 5 to both sides, which starts to get the absolute value part by itself, and the other side becomes a 15. And then the next thing we would do is divide both sides by 3. Do not distribute. So we would divide both sides by 3, and that finishes, getting the absolute value part alone. So now that the absolute value part is alone, we can split it into the two cases, where one case we're going to be equal to positive 5, and the other case we're going to be equal to negative 5. Okay? And now, and notice how it's two normal equations. We don't need the absolute value anymore once we split into the two cases. And now all we do is we solve each one separately for x to get our final two solutions. We would add 1 to both sides and then divide by 4. Same thing over here. We don't need to repeat that for like the millionth time. We've done this kind of thing a million times. So your final two answers here would be 1.5, 1.5, or negative 1. The next example is more of the same. I guess just I want to point out that in this example, it's already isolated. Like I don't need to do anything to get this absolute value part by itself. So we can go right into the two cases, splitting it into two cases. In the one case, the 2p plus 5 is going to be equal to positive 11. And in the other case, it's going to be equal to negative 11. So you literally write that out, dropping the absolute value in the process. And then we just have to solve each one separately, like we've done a million times. And you should end up with p equals 3 or p equals negative 8. And so that's basically, to summarize really quick, we're going to skip this, and I'll tell you that in a minute, but I'll tell you why in a minute. But again, it's absolute, or isolate the absolute value if you need to, right? Here, you needed to do a little bit of steps, beforehand, because we needed to isolate the absolute value. Here we didn't. It was already isolated. But once it's isolated, you can split into the two cases. The positive case, of this number over here on the other side, or the negative case. And again, like this is just integrated 1. There is a little bit more to the story. There's other curveballs we can throw at you in certain problems. But we're going to stick with the basics in Integrated Math 1. So this problem, we don't need to talk about, you'll talk about this sort of thing in maybe Algebra 1, where this is a little bit of a different sort of weird problem. So we'll just kind of skip over that, and you can worry about that in Algebra 1 class and stuff. So let's move on to inequalities. Specifically, the less than type first. So here's a basic starting example. What if it was the absolute value of something, like absolute value of x, was say less than 5? What kinds of numbers would fill in for the x and to make sense? Like the absolute value of what would be less than 5? And you might be thinking, well, the absolute value of 4 is less than 5. The absolute value of 0 is less than 5. The absolute value of 3 is less than 5. But what about like the absolute value of negative 4? Isn't that also less than 5 once you take the absolute? Well, you know, that's not that mysterious, so like why? But how about like the absolute value of negative 6? Is the absolute value is negative 6 a solution? No, because the absolute value of negative 6 would be 6, and that's not less than 5. Essentially, we're talking about anything between negative 5 and 5, which when you write it in like math lingo is like this. And yes, the word is and for a reason, because of the whole in-between thing. It's got to be like any number that wants to satisfy this inequality has got to be less than 5 and greater than negative 5. Like it's got to be in between negative 5 and 5, hence the word and. And that's basically how this is going to work. You know, we can split it into these two cases, where in the one case it's going to be just less than 5, but in the other case we're flipping it to a greater than, but we're also changing the 5 to a negative 5, and that's going to be the norm. So in this situation, you know, and once again, the whole isolating the absolute value is going to be important. So here, it's isolated, you know. So this 2x minus 1 quantity basically needs to be, you know, less than or equal to 5, but at the same time greater than or equal to negative 5. So you notice in green here especially how the split, you know, resulted. You know, when you split into the two cases, because, you know, absolute value, two vertical lines, two cases. And in the first case, we stick with the whole less than or equal to 5. But in the second case, we not only reverse the symbol, but we turn the 5 into a negative 5. And that's going to be like a pretty good overall strategy when you're dealing with absolute value inequalities. And spoiler alert, you're going to see that if the original symbol is greater than, same thing, but let's not get too ahead of ourselves. Let's look at this example. Okay? Absolute value of all this, 3x plus 2, is less than 8. And so, do you think this absolute value part is isolated on its one side? Yeah. You know, the absolute value is the only thing on the left side, so we can go ahead and do the split into the two cases, where in the one case, 3x plus 2 is going to be just less than 8, but in the other case, the 3x plus 2 is going to be greater than negative 8. Okay? And the word is going to be and for these less than problems. So for less thans, or less than or equal to's, the proper word to connect them is going to be and. And once you do the split, you can just solve each one separately, which I don't need to reteach. We've done this a million times. And so once you finish solving each one for x separately, we find that at the end of the day, x needs to be less than 2, and x has to be greater than negative 3 1/3. So these pretty much always come with a graph for your final answer. And so here we go. We got x is less than 2, open circle, and greater than negative 3 1/3. And the word is and so it's no surprise that the graphs are going into each other, and we're doing like this in-between type answer. I mean, look up here when it was like really, really simple. The absolute value of what numbers are less than 5, you basically end up with like anything between negative 5 and 5. And that's just how the whole less than works in this absolute value situation. So absolute value less than, the word is and properly, and the final graph should then look like this with the whole in-between type deal. But with greater thans, think about this. The absolute value of what kinds of numbers are greater than 3? Well, so now if you plug in numbers like 4, like 5, 6, 7, 8, 9, 10, and so on, that works. But so does numbers like -4, -5, -6. Because if you take the absolute value of -4, that's 4 and that's bigger. So now it's not really an in-between type thing. You can be, a number that's larger than 3, but also, or you could be less than -3. And if you notice, especially here, when it comes to like writing it out in math lingo, a very similar thing happens. It's two different cases. Here the word ends up being or, that is appropriate to use. Here it's or. And look, you split it into two cases. On the one case, you're just still greater than 3, but on the second case, you reverse the symbol and the positive 3 becomes -3. And that's a very good rule of thumb. So here, I don't care if it's x or something a little more complex like 2x minus 4, it doesn't matter. If the absolute value is isolated, you can split it into your two cases, where in the one case, let's focus more over here, I guess. In the one case, the 2x minus 4 is going to be greater than or equal to 2, just like as is. But in the other case, the 2x minus 4 is going to be less than or equal to -2. And that's just how you're going to split it up. In the second case, once again, sorry to be a broken record, reverse the symbol and make that +2 -2. All right? So moving on to like an example that you may or may not want to try on your own and pause the video and stuff. Again, just like back here with the equations, there's a lot of common themes here, but the very first thing you want to do, if necessary, is make sure you get rid of anything that's on the same side as the absolute value part. But again, it's another problem where like we don't have to do that. The absolute value of w plus 2 is all alone, and so we can go right into our split into two cases. In the one case, it's just going to be greater than 5 as is, but in the second case, it's going to be w plus 2 is less than -5. And just like we've been doing, right? Once you split into the two cases, solve each one separately. The appropriate word here is or, just because of the way greater than works. It's just the nature of it. That means like your final graph, they're going to be running away from each other, Greater than 3 or less than -7. The appropriate word here is or, with the graphs running away from each other. Okay? And so that's how that problem finishes out. And these other guys, once again, this is not Algebra 1. It's Integrated Math 1. We're just introducing you to this whole topic, and we're just going to focus on trying to get a really strong grip and mastery of the basic problems. Stuff like this, not going to go into it. I'm sorry for the mystery, but this is a different sort of plot twist, and you're going to get into like the special case stuff maybe in Algebra 1, but for right now, keeping it simple like this. And what we have here is just a pretty good, very wordy and everything summary, so just kind of like wrapping it all up, where your first step is you're going to get the absolute value part by itself if necessary, if necessary. And then you're going to split into two regular equations or regular inequalities. And you just got to remember how those two different cases are supposed to go. And when it comes to inequalities, and then you're going to solve each one separately right down here. But when I'm going to highlight something here, when it comes to inequalities for absolute value, if the original inequality was a less than, then the appropriate word is and. If it was greater than or more than, the appropriate word is or. So it's a decent memory trick to say like more means or, less than and. Again, when it's more than, the appropriate word is or. When it's less than, the appropriate word is and. It's just the way it goes, man. And that is section 6.6 in a nutshell.